Okay, so what I want to do quick is just a follow-up video to our previous one with basic file handling and moving this one into our basic file input output. So this is going to be doing with actually using read and write to move data from files to our standard input output streams and just being able to manipulate data in the files themselves. So without further ado, let's go ahead and hop over to the slides and take a look. So again, just some basic file input output. And the first thing we're going to do is look at the standard user IO. So we won't deal with actual file manipulation in terms of like making text files or anything of that sort quite yet. First, we're going to deal with just kind of like this programming paradigm's version of like cin, cout, print, scan, stuff like that. So if you're used to traditional C, then you've probably used scanf and printf as means of taking input from the user and printing output to the user as well. We are not going to use either of these because honestly, they are not the best. They're not bad by any means. I actually, when it comes to basic output, if you're comparing like printf and cout, I actually vastly prefer printf as a function because I like being able to format strings with placeholders and whatnot, as opposed to just stringing a bunch of cout statements all over the place. I think it's pretty good. We will not be able to use it directly as a means to stream to stdin and stdout though. So we will be using read and write. Now, I will also go ahead and say we can use read as a means of supplanting scanf. For what we'll be doing in this course specifically, the assignments and whatnot will not actually read user input during the runtime of applications. And I will talk more about that in a future video. But this is a way of doing it, and we will use read pretty frequently when it comes to reading directly from files, but not so much from the actual input stream during active runtimes of applications. But the way that it works, it's kind of like so. So I have the man page as always. I have the PDF, everything linked in the description, but read is used to read from files. Like, it's very descriptive and straightforward. As I stated previously, the input output streams, those are files in a Unix system. So we can actually utilize this as a means to read from it. So the way it works is we have three parameters. We have the file descriptor, a buffer, and a count. So the file descriptor is going to be, we need to open an entry in our file descriptor table, and that is the file that we will be reading from. It needs to exist in the file descriptor table, so that's why you typically usually need to open it first. More on that in a second. The buffer is essentially a character array that we're going to initialize in memory, and that is where we will read our data to in memory. And then count is the length in bytes of data to be read. So let's say if I wanted to read 20 bytes, I would actually put that particular number directly in there and it would read 20 bytes of whatever file I want to read into that buffer. So it returns the number of bytes read on success, returns 0 on reaching end of file, and then returns -1 on error or signal interrupt. But if you look at the actual sample code, you'll notice there's no create or open line in my code, yet I'm still able to read. And why is that? Well, from the previous video, as I said, every single process has the first three file descriptors. That's the standard input, the standard output, and standard error. You don't have to manually open those. They exist in every single process ID. So the moment that you start up a C application, they exist already. You can interface with them directly And if you're, I forget which one of these, I think it's in one of these three that has access to these kind of placeholders, a standard in file number. That basically equates to the static number 0. It's just a nice English written way of defining the standard input string. So that is what's happening here. It's reading the standard input. I have created a character array here named inBuff of buff size, which I almost always will define a buffer size towards the top where I'm including my header files. Now, before I move on, I am going to default buffer size to 1024 bytes pretty much the entire course for a lot of things. That is technically heresy when it comes to a lot of systems programming. Typically, what you would be doing is malloc and things of that nature, but that is adding an additional depth layer, whatever you want to call it, to this whole process. So for simplicity's sake, I am going to use static size buffers. I am going to make them long enough, that's why it's such a large number, that it is not going to be an issue of overflowing data. 1024 is generally a pretty decent buffer size. You might see 512, 256, generally powers of 2. You're going to see them pretty frequently here. I'm going to go 2024 just because I have a modern system. I've got plenty of RAM. It's not the worst thing, but when you're dealing with low-level code like this, especially if you're embedded, doing things like this, that 1024 could be a large chunk of memory for the overall scope of things, so it may not be the best. And again, it's not the technical correct way that this should be being done. It is sufficient for what we are doing right now, because we need to have at least a decent enough length to read data into. And for the purpose of this course, I am not going to be doing anything of substantial size that would require going over 1024 bytes for any actual buffer. With all that being said, this is the buffer that I'm reading my data into. And then that is the size of it, essentially, that I want to actually read. Now, one other thing is when you call read specifically, that guy right there is going to halt program run. You're going to type in whatever text that you want, and then when you hit enter or return, that is whenever read will finish. And it is going to take that enter/return as entering a new line character. So if you want to properly have that as a string in C, what you can do is you can replace the new line character that you read with a null character, and all of a sudden now you have a null terminated string. So you can see the string, this actually stands for string complementary span. I'm going to shorten it to string cspan, and technically it is going to read this character array, this character array, which for me is just going to be a single character because all I care about is reading up to the new line character. And that's how many bytes it's read, that's the location it's going to have. I just want to replace that new line character with a null terminated character, null character, to give me a properly null terminated string. Is that more than I need? Yeah, but it's just kind of a safe practice to have a null terminated actual string from read. Now again, for all the things I'm going to be doing assignment wise, you won't ever need to read from standard input. That's just not common practice in a lot of systems programming. A lot of that is going to be passing data in through command line arguments. I'll get to that in a later video. For now, I just wanted to show how this works whenever you can't do things like scanf. You can do things like this. It's just typically not common practice and not the best practice to do so. Write, however, this is perfectly fine. This happens all the time. So, just like read, that was used to read from files, write is used to write to files. Shocking. Same thing, file descriptor, a buffer, and a count. So we have a file descriptor, a file to write to, the data we wish to write to a file, and then a count, length of bytes, length of data to actually write. Returns the number of bytes that were written on success, return 0 when reaching the end of file, and -1 on error. Again, this is almost the exact same thing as read, it's just a different direction essentially. So in the most simplistic example, I have initialized a string character array called outbuff of just hello world with a new line character. And then what I have here is I'm using string length on outbuff to get the actual length of that character array. And then I do write using standard out file number, which is going to be a nice English written way of just the character 1, because this is a file descriptor entry for the standard output, because it's always there for the first 3 actual entries, the actual buffer I wish to write to this file, and the number of bytes of this buffer that I want to write to the file. So I use string length of the entire buffer to give me the number of bytes in said buffer. So I'm going to write the entire thing, and this is literally just the equivalent of doing hello world at systems level C. And that's about all this example is, which is fine. So we covered standard input and standard output. There is that third one of standard error, and that is an error output stream. This is used separate from your standard output, because standard output is just where your default text gets sent to the user. If you want to do any actual proper error handling and whatnot, then you would send it to a completely different stream. So you can process those two things completely separate. Now, I could do write, and instead of doing standard output file number, I could do standard error file number. That would work. There is p error, and I think from what I can read online, p error in the modern day is signal thread safe. To my understanding, there has been a long history where p error, or the error number itself, was considered to not be thread safe. But I think currently the error number variable is thread safe. And it gets kind of really funky in how that works, because the error number variable gets set whenever, well, I mean, when errors occur. Like if you saw on the read and write, it said -1 gets set on error or a signal interrupt. In addition to that return, it would set error number to a specific value to indicate to the system that a system failure occurred. If you use p error in a manner that you manually create your own error, so like if you didn't have enough command line arguments, or some data that was passed in through a value, like a file that was supposed to be a certain value is not correct, and you specify that it's your own error and not specifically a system error, you'll often see it output success in addition to whatever else you actually have. So it's going to have this text and then a bit more text after that. The p error open to read here would print out whatever I want it to be, and then the actual system failure after that. So if you ever do p error of your own manual errors, and you see success after the failure that you wrote out, that is just indicating that there is not an actual system error that was encountered, because that is different than just, oh, the program I wrote had some data that it wasn't expecting, or I didn't want the user to do something a certain way, so I basically safely halted execution and put that out into the error stream and everything. And that's perfectly fine. But a lot of people get confused on, why do I see the text I want from P error followed by success whenever I want to indicate failure? That is just saying your system did not encounter a more, I don't want to say catastrophic error, but like if you are encountering like a open error here, this -1, that is an actual system error, not something that you defined in your program. So it's something system level that had an error. So that error number is indicative of that. And P error is just a sane way of handling the P error stream, along with returning whatever is indicated by the error number. You can find a lot of them in this man page, and then you'll also find a lot of them in whatever system call man page that you look at as well. So if you go back to the read and the write one, even the open and close ones, you'll see that they will set error number according to however that actual system call is supposed to designate their errors. This part right here is honestly very complex, and that is why a lot of this thing has been considered system or signal unsafe for a while. But I think in modern day it's completely okay, just a tad bit confusing. But honestly, if you get some practice using it, it's generally not too bad. Moving on, we go back to read and write. This time, instead of dealing with standard input output, we are dealing with actual file I/O. So we're not going to introduce anything really new here. It's just using it in tandem with actual files in your file system. So as before, read function will be used to read data from our standard files. We need a buffer to read our data into, and return the number of bytes read for later use. Read does not add a null terminator. Very similar to whenever I was adding a null terminator to the system input read. When you read from files, it reads a specific number of bytes, and that is it. It does not add its own null terminator at all. You have to manually do that. And that's what I do right over here. So again, I define my buffer size. I create my actual input buffer. Again, I am just doing static buffers. I apologize to people who are more familiar with C that don't like that. I know it's not good. It is just as a means to show how these work, not a means to show how the absolute most peak excellence of C code is. Essentially, it's just trying to illustrate how some of these system calls work. I know that this is bad practice. I'm very well aware. So, beyond that, we have the file when open, which is sample.txt. We're going to open it as read-only. So we use open, and then we set our file descriptor, and we just call it fd1. It's the first file descriptor we have, first file we open. That's okay. Number of bytes we want to read is read file descriptor 1, which is, again, sample text in the file descriptor table. Nbuff is the actual buffer that we want to read to. And then buff size is the actual number of bytes that we want to read. Now, we don't have to read all of them. It'll read up to that many, up to an end of file, and it will return the actual number of bytes that was read from the file as an integer. That's really, really nice, because since read does not place a null terminator, we can use the input length, the number of bytes that was read, as the actual place in our character array of where to place a null terminator. And it will place it directly after the last byte in that character array. And once we do that, we have read our data. We will then want to close the file since we are done with it. And then what I'm doing here is I'm just writing in buff, in length to the actual standard output. So I'm just writing back to the user what I read from the file. And that's pretty much it. Moving on from there, we have write. We do not use unique buffers to write files, just the unique file descriptors for which files we want to actually write to. So what does that mean? Well, right here, I create my character array of hello world. Much like I did with the standard output one, I'm just going to write the same hello world out buff. I'm going to write that to actual text files. So I'll do the same thing, get the string length of that entire buffer. I am now going to use the create system call to make two text files, sample1.txt and sample2.txt, both using our standard 644 permissions. That way the owner can read and write, the group can read, others can read, just standard file permissions. That's file descriptor 1 and 2. So now we have two file descriptors. So now I have two write calls. Both are using outbuff and buff length that I did right up here, but the difference is I am using file descriptor 1 and file descriptor 2 as we made two file descriptor entries. Once I am done actually writing them, I will close file descriptor 1 and file descriptor 2. Again, if you're going to open a file, you do what you need to do with it, whether you're reading it, writing it. Whenever you are done with it, you close it. It's just good practice. And then that is it technically for like read and write and the idea of what's happening here. But there's a little bit more happening behind the scenes that's not exactly the script or obvious right out the gate. So each file descriptor has a file offset that represents the number of bytes from the beginning. So as you've noticed, whenever we're calling read and write, we're reading up to the actual number count that we pass as that third parameter. Well, what happens if I have a long enough file that it exceeds the actual number of characters that I'm reading? So like I'm using 1024 bytes for all my buffer sizes, right? So what happens if my file is longer than that? Well, you can read things in chunks. And whenever you read multiple times in a row the same file on the same file descriptor specifically, it will do, let's say, here's a file, here's 1024 chunks, right? And then if you read again, it'll have the offset directly after. Now you're reading the 1024 chunks, and you'll continue to do this over and over until eventually, let's say this is only 512, and you eventually get to the end of the file, so EOF essentially, and that would be where that stops. But that file offset is automatically incremented so many times over and over. And the same thing happens with write. If I need to write multiple buffers, then I will write and the offset will be automatically increased to the end of that point. You don't have to actually manually do that, which is really, really nice if you need to read large files or write large amounts of data. So in this case, let's see, I have again my 1024 buffer size. I have an end buffer of that same buffer size. I'm going to open sample.txt in read-only mode. I initialize the read length to 0, and now we read 1024 byte chunks of data from the file until the entire file has been read. So while read length equals read file descriptor 1 in buff size, and that's just a read that we've been doing, while it's greater than 0. Why greater than 0? This is essentially EOF. So while we've not reached the end of the file, we will just continuously read, and then read length will be the number of bytes that we actually read. Okay, so use the previous number of bytes read, and we will write to the standard output what we just read from the file. So all I'm doing here is I am just writing to the standard output the entirety of sample.txt, no matter how large this file is. So this could be 12 gigabytes. This while loop, sorry, didn't mean to do that. This while loop here will read until it gets to the end of the file. 1024 byte chunks at a time, read 1024 bytes, write that to the output. Read another 1024 bytes, write that to the output until it finishes out the entire file. Once it does, we'll close it and then we'll exit our program. And that's how you would handle that. Now, we can use this to copy files, which is honestly really, really nice. We're using that same process. So since each file descriptor has its own file offset, we can easily copy a file of an unknown size chunk by chunk from one file to another. So instead of taking those chunks and writing them to standard output, we could instead take that copy that we read and write that to a separate file. This is very, very similar to the cp command that you use in Linux. So since we read the data to a buffer in memory, we can easily copy this to as many duplicate files as we want to, just by adding more file descriptors to our loop. So again, same thing, 1024 buffer size. We have an actual input, an input buffer essentially. And then we have our file descriptor 1, which is used to specifically open sample1.txt. This is the file that already exists that we want to read. That's why I'm opening in read-only mode. The second file, I am creating a new file that I want to copy the data from sample1.txt to sample2.txt. So I'm making an entirely new file. My goal is to take all the data from sample1.txt in that 1024 while loop, and then instead of chunking it out to the standard output, I'm going to chunk it out to sample2.txt. So again, read length equals 0. While we're reading it, while it's greater than the end of file, instead of standard output here, it's now file descriptor 2. So it is a very, very minor change here, that I am just redirecting the output stream of data from standard output to the file that I created here. The only thing that really changed is this input for my write command. Again, once I'm done, I close both files and we move on. So this part is where things get a little bit more interesting per se. This is processing files line by line. There are very, very many ways of doing this, and this is one of the ones that I tend to like to do. So we can use a bit of clever logic along with pread as a means to process our file one line at a time. This allows us a nice way to handle the file of each line as its own entry, so its own kind of buffer. Both pread and prewrite are the same as our existing versions, with the added ability to specify their own offset. So instead of that manual offset that just automatically increments itself by how many lines, how many bytes were written or read, we can be in control of that offset. That means quite a lot. So let's look at this. Same thing, 1024 bytes. Same nbuf. I open my file. Nothing's really changed. I have a read length of 0. However, I now also have an offset of 0 because I want my offset to be at the very, very start. Same while loop that we're used to, reads 1024 byte chunks of data from the file, starting at a custom offset until the entire file has been read. Now that right there is fairly interesting. So read length equals pread instead of just basic read, file descriptor 1, the sample.txt from earlier, an input buffer that we already have and buff size that we're used to, and this time a fourth parameter of offset, which we already have as 0 right here. And again, is greater than end of file. So we get the number of bytes up to the first new line character. So input buffer is going to be that 1024 bytes. And in that 1024 bytes, maybe we have a bunch of actual lines, right? Maybe they're all like a 12, 256 new line, and then here, I'll just do this one, 12, 0, 1026. So just a bunch of random characters all followed by new lines. So just individual lines of data. But if we read 1024, we might have read in like 98 lines of code or text. But we want to process that line by line. So what I'm going to do is use that same string C-span from earlier to read up to my first new line character. Because if I look back at that, I had like 12 new line. It doesn't matter what comes after this 256. What I did is took my input buffer, and then I just want to like isolate this first line. So I get the line length of that, and I adjust our offset for p-read to 1 character after a new line character. So my new offset, instead of being like the 0 starting here, it'll be starting at this 256. So even though my original read has this large chunk of data, I want my next offset to not be way down here after all of what I just read. I want it to be 1 character after my first new line. So whenever I start reading again, I'm not here, I'm right here. So now my read would just be here. So it lets me go 1 line at a time, because then it'll be the next time we then right after this new line character, after this new line character, so on and so forth, until we get to the end of the file. So that is the goal there. So then we create a buffer to store a string. That is creating a line buffer. So again, we have the input buffer, which takes in the entire 1024 bytes. That's great. I get my offset for the next read, but then I need to do something. I need to actually pull out the line to a new buffer. So I create a separate line buffer, and then I string number copy specifically, because that's definitely more safe than just basic string copy. This is where I want to copy the data to. So this is my destination. My source is input buffer. That's at 1024 bytes. That's the whole chunk of data. There is an external buffer over here, but it's the line. And then I want the few bytes right here up to the first new line character to be copied over here. And that's the actual line that I want to work with. And then, like I've been doing previously, I manually add a null terminating character to get a proper C string out of that. So I'm just pulling up to the first new line character out of my entire input buffer into a separate line buffer, adding a null terminator, and I work with line. And then it will continue this process until we reach the last line, and that's how we can process a file line by line. Now again, there are many ways of doing this. I think this is a good way to demonstrate how the offset that you typically don't really notice very much works. Because with basic read and write, it automatically handles the offset for you, just putting it at the end of the last number of bytes that you read write. But with p-read and p-write, you get a chance to actually manually, I guess, allocate how much you want to actually read, or where you want to start reading from. And this is a pretty good way of actually practicing that. So that is just basics of read and write. Again, we've done with the standard input output. We did it with basic files, showed how the offset works, and then also did some manual offset manipulation with p-read and p-write. That is honestly a lot of information all at once. That's why I separated this video out for read and write from open and close. So they're two separate videos, because if they were all one, this would just be an absolute info dump. I do have more to add on to this topic. I'm going to save that for a separate video. But at the end of the day, I hope all of this made sense. I really hope you learned something and take something away from this. And at the end of the day, I hope this is helpful. That's all I got. I'll see you guys next video.